Hello. I think we're going to get started here. It's about past 8:30. I was just waiting for the sky to get dark enough because this is, a rather visual presentation since it's about the aurora. So I wanted to make sure the projector was bright enough to actually kind of see some of the details and intricacies of what we're going to be looking at here. So it looks pretty good now, so I guess we're going to get started. Welcome to the July edition of Second Saturday Stars. I am Mark Polanski, a volunteer and astrophotographer here at the McCarthy Observatory. And tonight I'm going to be talking about all things aurora. Mainly I'm going to try to describe what the aurora is, what does it look like, and what you should be looking for if you're trying to see it. Where does it come from? What are the ingredients needed for aurora to occur? How and why does it happen? Recent scientific papers have uncovered more details about what actually drives the aurora. And when and where can we see it? Meaning both us specifically here in Connecticut and around this latitude, and more generally, what are the best places to have a chance of seeing it? We'll start with what is the aurora. Simply put, it's a naturally occurring light show associated with a geomagnetic storm, sometimes visible to the unaided eye. In the northern hemisphere, it's called aurora borealis, or the northern lights. In the southern hemisphere, it's called aurora australis, or the southern lights. It can take the shape of broad columns extending up into the sky, or a sea of waves and ripples with red, green, blue, and pink hues. Sometimes it moves quickly, like flames in a campfire. Sometimes it builds slowly, or is just a fixed glow in the sky. No matter the color or shape it takes, it can be a real treat to see under the right conditions. It is important to have realistic expectations, though. Unfortunately, our eyes are not great at seeing color in low light conditions. Cameras are much more sensitive to color detail because they can collect light over time during a long exposure. They do a much better job of showing off what faint things look like that we might not be able to see with our eyes. If you've ever looked at a nebula or a galaxy through a telescope, you'll have likely seen them as more of a gray, kind of bluish, dull color, more like a blob than an actual thing. Distant deep sky objects look much less dramatic by eye than they do in pictures. And the same can be true of the aurora. They do have the possibility of having some bright visible color, but only under the right conditions, which I'll explain in a little bit. For the most part, especially for more southern latitudes, you're more likely to see it as kind of a patchy gray or maybe a light green sort of blob or a couple of lines moving around in the sky. Where does the aurora come from? The simple answer is the sun, and magnetic fields, and the small amount of gas in the fringes of Earth's atmosphere. Earth has a lovely molten iron core, which generates a reasonably strong magnetic field around the whole planet. If you've ever used a compass, you've seen this magnetic field in action. Earth's magnetic field is a donut-shaped, layered like an onion, elastic bubble wrapping around the entire planet. The north and south poles form the donut hole, and a thicker outer circumference of the donut wraps around the equator. The magnetic field is like a shield, protecting most of Earth from the perils of the solar wind, a steady stream of plasma from the sun made up mostly of electrons, protons, and alpha particles. The solar wind travels out from the sun in a relatively steady stream at about 1,000,000 miles an hour. It takes about 4 days for freshly emitted particles from the sun to reach Earth. The solar wind pushes against Earth's magnetic field, causing it to squish in on the sun-facing side or daytime side of the planet, and it stretches on the night side as it blows by. Sometimes the sun burps out extra plasma at much higher speeds. These burps are called coronal mass ejections, or CMEs. The sun has its own super strong magnetic field, and the extreme environment in the outermost layer of the sun's atmosphere, called the corona, leads to constant tangles and knots within this magnetic field. These tangles and knots form structures called flux ropes, and they behave like elastic bands stretching and twisting out from the sun, sometimes carrying enormous arcs of plasma. Sometimes they become too stretched or too stressed, and just like rubber bands, they'll explosively snap in a process called magnetic reconnection, where the magnetic field breaks apart and reconnects back into the corona. All of the plasma built up in the flux ropes gets slingshotted out into space as a coronal mass ejection. These disturbances are usually associated with sunspots, or active regions visible in the deeper layers of the atmosphere of the sun, the chromosphere and the photosphere. Occasionally, a coronal mass ejection is pointed in just the right direction to hit Earth. Usually it takes about 1 to 4 days to arrive. Some of the more energetic events can move much faster, taking as little as 15 to 18 hours to get here, much faster than the usual 4 days of the solar wind. Keep in mind the sun is about 93 million miles away, and these things are enormous. In this video of a recent CME from 2023, that little blue dot just to the left of the CME is Earth. That's how big Earth is relative to the sun. Look how big that plume is coming off. Fortunately, Earth's magnetic field safely deflects or steers away most of that solar plasma around the planet. Otherwise, Earth might end up like Mars, where the solar wind has slowly stripped away the atmosphere, leaving it as the dry and barren planet we know today. Sometimes solar plasma can get caught in the magnetic loops and layers of the magnetic field and get sent straight to Earth's poles. The material is coming from the direction of the sun, so it's going to interact with Earth on the sun-facing or daytime side of the planet. This can generate some amount of aurora, but it's happening on the daytime side of Earth, so it's not really visible. So it's called daytime aurora. So yes, aurora can happen in the daytime, but we can't see it because the sun is too bright. Things get way more interesting on the night side of Earth. If you remember that picture of the Earth's magnetic field from earlier, you might have noticed the daytime side, or the sun-facing side, has a more squished look for the magnetic field in the front, and the nighttime kind of has a shorter, more stretched appearance. The incoming plasma from the sun, from both the solar wind and CMEs, push against or squish Earth's magnetic field on the daytime side. As the plasma is deflected and wraps around past Earth, it stretches out the magnetic field on the night side, like long hair blowing in a strong wind. The stronger or more energetic the CME, the more this compression and stretching can occur. With enough plasma and energy, the stretching can cause layers of Earth's magnetic field on the night side to pinch together and snap in a magnetic reconnection. It's the same process that causes the flux ropes to break on the sun and release the plasma to start this whole process. The animation on top shows an incoming wave of plasma from the sun impacting our magnetic field, appearing in red. The sun-facing side squishes in, and the remaining plasma is deflected around the planet. When strong enough, it pinches the night side or the back side of the magnetic field into reconnection. The snapping of the magnetic field layer causes the solar plasma to ride the lines of the magnetic field as they reconnect to Earth, and they directs the plasma towards the north and south poles. The more intense the solar storm, the more this can happen, the more energy is directed back towards Earth, reaching lower and lower latitudes, meaning aurora can occur further south. The bottom animation shows the deflected plasma getting caught up in the backside of the magnetic field, called the magnetotail, after a reconnection, and shows how it gets redirected to the poles, causing the aurora. But that's not the whole story. While the particles in the plasma are moving very quickly as they wrap around Earth, they have to accelerate to ridiculous speeds to have enough energy to trigger the aurora. And it wasn't until recently that we confirmed how this happens. In 2021, a research paper was published by Jim Schroeder, a physics professor at Wheaton College in Illinois, linking this acceleration to Alvin waves. Alvin waves are a type of plasma wave where ions oscillate in response to tension along magnetic field lines. These were proposed in 1942 by Hans Alvin, and this phenomenon also explains why the corona, or the outermost layer of the sun, is actually hotter than the surface or inner layers of the sun, the photosphere. The extra energy comes from the interaction of magnetic fields, fluids, and electric currents in the extreme environments of the plasma. When solar plasma encounters magnetic reconnection on Earth's magnetic field, the particles can basically surf on the Alvin waves along the lines of the magnetic field, giving them a huge boost in speed as they enter the atmosphere. The electrons in the solar plasma can be accelerated up to 45 million miles an hour by the Alvin waves. The top graphic shows the path the particles take from the point of the magnetic reconnection back to Earth. The animation below depicts how an electron can surf along the wave. One important mechanic of all this is that the electrons must be going at just the right speed to catch the wave and accelerate, just like the red electron does in this animation. If it were moving just a little bit slower, the wave will just brush right by, like it does with the gray electron. I've never been surfing in the ocean, but I've heard that's kind of how surfing in the water works too. If you're too fast or too slow, the wave will just pass you by. But if you catch it at just the right speed, it can take you for a ride. And this is really important to how the aurora actually happens. Once accelerated, these superfast particles come raining down into the upper fringes of the atmosphere, crashing into the atoms of oxygen and nitrogen, as seen in the image on the right. These collisions cause the atoms to become excited, reaching higher energy states. And the exact energy state of each individual atom determines what colors we end up seeing in the aurora. So the next two slides are pretty technical in terms of chemistry. So here's a quick summary of what they're going to end up talking about. Basically, atoms are excited by the incoming solar plasma, and they release light when they relax back to the resting state. Green light ends up coming from atomic oxygen at lower altitudes in the atmosphere, relatively speaking. And this is still relatively high up in space. It's still just past the Kármán line. And green is the most common light in the aurora, usually between 60 and 185 miles in altitude. Red light also comes from atomic oxygen, but at much higher altitudes, typically between 185 and 372 miles, and usually indicates a particularly strong geomagnetic storm. Blue and pink can come from nitrogen at lower altitudes, typically just below 60 miles. So getting into the weeds, if we go back to chemistry class, we know that atoms are made up of protons, neutrons, and electrons. Protons and neutrons make up the nucleus of an atom, and the electrons float around them in orbital shells. We also know there are different energy levels within those orbital shells. As an atom gains energy, sometimes more electrons can enter the orbital shells, or electrons can leave the shells, making the atom positively or negatively ionized. Other times, electrons within the shell can jump from one state to another, like from an inner shell to an outer shell. When the excitement ends, the electron goes back to its lower energy shell, or if it's ionized, it'll release the electron. It's like if you're at a sports game, sitting in the stands, and something really exciting happens, like the home team scores a goal or whatever. People tend to stand up and cheer loudly for a short amount of time. And then after the moment passes, you'll sit back down. That's kind of what electrons do when something exciting happens. Thing is, electrons under the right conditions, when they sit back down, they can spit out a photon, which is what our eyes or cameras can see as light. In spectroscopy, there's something called a forbidden transition that describes a spectral line, or a specific frequency of photon emitted, when an excited atom spontaneously drops to a lower energy state. For certain energy configurations, this transition can take up to a certain amount of time. In the atmosphere, the less time it takes, the more likely it is that it can happen. Energetic atoms tend to be rather fidgety. They don't like being excited for very long. Bumping into other atoms or particles at lower speeds can relax them without releasing the photon. But if an atom is left alone for long enough, it will eventually calm down and release the photon. This whole process has a direct impact on the color of the aurora, as it relates to how dense the atmosphere is at different altitudes above Earth. Green is the most common color of the aurora, as it comes from atomic oxygen excited to the 1s state. As it relaxes to the 1d state, it releases a green photon. It only takes about 1 second for this transition to happen. At altitudes between 100 and 300 kilometers beyond the Kármán line, the density of the atmosphere is very low. There's only a few hundred atoms per square centimeter. Even at such a relatively low density, the likelihood of atoms bumping into each other to calm down is still pretty high over time. But many of the oxygen atoms are able to calm down within that 1 second and release the photon of green light. For atomic oxygen, 1D is still an energetic state. 3P is actually the lowest energy state for a single atom of oxygen. Transitioning from 1D to 3P will emit a red photon. But this can take up to 2 minutes to happen spontaneously. In the 100 to 300 kilometer altitude range, this is a very low probability event, because the density is high enough that the atoms are likely to bump into something before that 2 minutes is up, and they'll end up relaxing without giving up a red photon. As you go up higher in altitude, past 300 kilometers, the density of the atmosphere drops to a few dozen atoms per square centimeter. Past that point, the density is low enough that the oxygen atoms at 1D have a much better chance of lasting that full 2 minutes it can take to relax back down to 3P. That means red aurora come from oxygen as well, but from much higher altitudes. At those higher altitudes, the density is so low, it usually takes a higher concentration of solar plasma to get to that excited state to increase the chances of oxygen atoms getting hit. So higher altitude red aurora are a sign of a particularly strong solar storm. As I saw on May 10th, the photo on the right here was pointing my phone basically straight up above me towards the zenith. I've never seen red like that before, especially directly overhead. Blue and pink are usually the result of ionized nitrogen coming down from a 3D state just inside the Kármán line under 100 kilometers. The pink coloring usually comes along the bottom edge of a green, as it's usually the same stream of particles impacting oxygen and nitrogen at a similar altitude. I couldn't find any data on how long that transition takes, but it must be fairly quick in order to happen at such a low altitude. Past 600 kilometers in altitude, helium starts to dominate the composition of what's left of the atmosphere, and past 1,000 kilometers, hydrogen starts to take over as you enter the interplanetary space. These elements can be excited by high enough concentrations of solar energy as well, and they can appear as either a blue or a pink color. All the other colors of the aurora, like yellow and purple, are created by layering and mixing of the main colors, like red and green combine to make yellow, blue and red combine to make purple. So that's where the aurora comes from and how it happens. When and where can we see it? The best chances for a really good show are when the sun is active, meaning lots of sunspots, and chances for coronal mass ejections. The sun goes through cycles of high and low activity, called solar cycles. A cycle spans about 11 years, during which there's a steady increase in activity. We see more sunspots developing, more intricate corona, larger and more frequent prominences, solar flares, and so on. With more activity, there's a higher chance of a coronal mass ejection blasting material towards Earth. Humans started keeping track of these cycles in 1755, starting with solar cycle 1. Right now, we are in an uptick of activity heading for the peak of solar cycle 25, which is expected to reach solar maximum at some point in 2025, before steadily declining into the 2030s. That means the sun is likely to be very busy over the next year, which could mean more opportunities to see the aurora. In general, aurora are really not all that uncommon in far northern latitudes, like up in Canada, Alaska, Greenland, etc. Up there, even the solar wind itself can sometimes generate aurora. The short answer to where and when we can see the aurora is this: on a cloudless, moonless night, away from city lights, just before midnight, north of 55 degrees latitude. Seeing it is never a guarantee, of course, but it could happen as often as every couple of days at those latitudes. For reference, Connecticut is at about 41 degrees latitude. I've only seen the aurora 3 times in my life, all here in Connecticut. The first time was in June of 2015. Next time was 8 years later in April of 2023. And most recently, May 10th of this year. If we look back at the solar cycle chart, yep, that checks out. 2015 was near solar maximum of cycle 24. And from 2023 up until now, we're approaching the solar maximum of cycle 25. Cycle 24 was kind of a dud in comparison to the previous cycles, so scientists thought that cycle 25 might be a dud as well. But so far, the activity seems to be ramping up past the predictions. The energy, speed, and amount of charged particles from the sun affects how far south from the poles the aurora can be seen. More material coming in at higher energies has a better chance of pinching the magnetic field along lines corresponding with lower latitudes. The bigger and badder the CME, the farther south the aurora can go. On May 10th of this year, the aurora could be seen as far south as Hawaii and Florida. It was the most intense impact in decades, or at least since 2003. It was the first time I could actually see color and structures with my own eyes. And it was strongest right around 10:30 or 11 p.m. I got really lucky. Much of the state was blanketed in cloud cover, but for some reason I had clear sky at home, with just the right amount of fog settling onto the lake to create some stunning visuals. The May 10th event came courtesy of a sunspot group called AR 3664, with AR meaning active region. It was actually pointing just past Earth when the CMEs erupted, and this actually turned out to be multiple CMEs. There were 4 or 5 at a time, some of which combined on the way towards Earth. But in any case, we ended up with more of a glancing blow than a direct hit. I took both of these photos on May 7th, about 2 days before the CMEs were sent out. The image on the right is part of some experiments I was doing with film astrophotography, taken with Milford Delta 100 film, if anyone's curious. The image on the left is a close-up crop of the region with a more modern astronomy camera on the same telescope. The sunspot group was big enough to see without magnification. If you had solar-safe glasses left over from the eclipse in April, you could have likely seen the sunspot group with just those glasses. Being able to see and analyze sunspots like this can help us with predicting when the aurora might occur, as the spots are prime candidates for producing coronal mass ejections. The best resource to find out what's going on with the aurora and geomagnetic activity in general is NOAA's Space Weather Prediction Center, or SWPC. Right on the front page are indicators of solar activity measured by an assortment of spacecraft. For aurora purposes, the 2 boxes on the right are the most relevant. One is aptly named the aurora, and the other is the estimated planetary K index. The aurora map shows potential aurora activity up to an hour in advance, thanks to observations from spacecraft between Earth and the Sun. The circular blob of green shows visually where the aurora have a chance to be seen. As more energetic or higher quantities of plasma approach Earth, that green circular blob can grow and turn red, indicating a much higher probability of seeing aurora. Geomagnetic activity is described by the estimated planetary K index on a scale of 0 to 9. 0 meaning no geomagnetic activity at all, and 9 meaning extreme activity, and aurora are very likely to happen in many places. The planetary K index typically needs to be about 8 or higher to have a good chance of seeing aurora here in Connecticut. If you ever hear anything on the news about aurora, check this website for actual data to see whether you might see it or not. I've seen news outlets put out alerts for aurora with a KP of 6, when it really needs to be 8 or 9 to see it from here. Though with a very unobstructed view of the northern horizon, 7 might be a distant possibility. It would still need to be a near moonless, cloud-free night, with the best times of activity being from 10 p.m. to 1 a.m. And this is probably a good time to mention that solar activity isn't always good. It's not all harmless and pretty light shows. The Space Weather Prediction Center has 3 categories for impacts by solar activity, each with a scale of 1 to 5, with 1 being minimal effects and 5 being extreme or extensive impacts. Categories are G for geomagnetic storms, which typically result in the aurora, S for solar radiation storms, which are more dangerous for, say, the astronauts on the International Space Station or pilots or anybody riding in a plane that's up at cruising altitude, and R for radio blackouts, which means there's enough radio interference coming from the sun to potentially disrupt radio communications with airplanes, boats, anything that uses radio to communicate. That includes GPS satellites. So during a severe geomagnetic storm or a severe radio storm, GPS may just stop working. In September of 1859, the most intense geomagnetic storm in recorded history impacted Earth. It created aurora visible across the entire planet, reportedly bright enough that folks in the northeastern US could read a newspaper from the aurora light. It caused telegraph networks to behave in really strange ways. Operators were given electric shocks, relays were sparking and blowing up, and in one recorded case, operators were able to communicate from Boston, Massachusetts to Portland, Maine without a power supply connected. Normally, the telegraph were operated by batteries connected in series, and by closing the circuit, they were able to trigger the telegraph back and forth. They disconnected their batteries, and the electric field from the storm induced enough current in the long-distance telegraph wires where the equipment still worked without batteries. It's wireless power. Such an induced current would wreak havoc on our power grid today. Think of the lengths of wires crisscrossing all around the country. Such strong geomagnetic activity could induce enough current to overload switching stations and cause a cascade failure across the grid, leading to hours-long blackouts. Fortunately, grid operators have procedures in place for geomagnetic storms, and they can harden against them. And because the May 10th event was more of a glancing blow than a direct hit, while it created spectacular aurora, the other impacts were relatively minimal. Had it been a more direct hit, it's hard to imagine what the effects might have been. So that's the story of the aurora. It's a light show caused by geomagnetic activity, solar particles from the sun interacting with Earth's magnetic field. The charged particles come from the sun via plasma, both through the solar wind and from coronal mass ejections. The plasma impacts and compresses Earth's magnetic field, causing breaks that can accelerate particles into collisions with oxygen and nitrogen atoms in the fringes of the atmosphere. These atoms then relax and release the light we see as aurora. We have the best chance of seeing the aurora during periods of high solar activity, with the greatest chance after an Earth-facing coronal mass ejection. It would also need to be a cloud-free, moonless night with a relatively clear view of the north or northwest horizon. From Connecticut, the best chance to see anything is when the planetary K index is 8 or higher. So as we get into the peak of solar cycle 25, we expect solar activity to continue ramping up over the next year. So here's hoping for some good aurora. Thank you, and please join us August 10th for our next Second Saturday Stars here at the McCarthy Observatory. If you have any questions, I'll try to answer them, but I'm by no means an expert in this. Yeah, the magnetic field is known for flipping. The nice thing about having a molten core is the magnetic field is always kind of wobbling like this. It's kind of like a top. And I saw a chart of plotting the position of where the North Pole was magnetically over the last like 100 or so years, and it's kind of wandering. Yeah. A CME. It might be. Well, I mean, the field never completely dissipates. Like even in the process of flipping, like there's still no. It doesn't like collapse into itself and then reappear on the other side. It's kind of wandering like this. Yeah. Yeah, but it does take a long time. It could take thousands of years for that to happen. How's our sky looking? A little bit of moon up there. Yeah, there's a patch of opening here. See if you can see what direction the clouds are moving in. Looks like they're kind of heading southeast.
We'll have the big telescope open.
Yep, the big telescope should be open for viewing. It's our brand new plane wave telescope. As Monty said, it was just put in April of this year. So thanks for coming, and hopefully enjoy some views of the moon tonight.
Can CMEs affect the angular velocity of the Earth and our time of rotation?
Not directly, no, not nearly enough mass for that.
Not yet? Okay.
No, because that's more like Earth is still pretty heavy, so not enough mass for that to happen.